Hello everyone, in this multivariable calculus tutorial we will learn how to find the maximum, minimum and saddle point values of a function of two variables. And here's our function. The problem is, find the maximum and minimum values as well as saddle points of the function given by x to the power 4 plus y to the power 4 minus 4 times x times y plus 1. Here's the first step. The first step is to find the partial derivatives. First of all, we need to find this partial derivative, f with the subscript x, and that's the partial derivative of f with respect to x. Let's find this partial derivative. Obviously, from this equation we have 4 times x to the power 3, 0, minus 4y. Next, we need to find fy. That is, we need to find the partial derivative of f with respect to y. We have 0, 4 times y to the power 3. Over here, we obviously have minus 4x. Next, we need to find the mixed partial derivative. That is, we need to find f with the subscript xy. That is, we first take the partial derivative of f with respect to x, that is this term, and then we take the partial derivative of the result with respect to y. Consequently, we need to take the partial derivative of this expression with respect to y. And obviously the result is equal to minus 4. Next, we need to find fxx. Let's find fxx. This is basically the second partial derivative of f with respect to x. And let's do that. What do we see over here? That's basically 12 times x to the power 2. And finally, we need to find fyy. Fyy is the second derivative, partial derivative of f with respect to y. And obviously, from this expression, we have 12y to the power 2. Next, we need to determine the so-called critical points. The critical points are actually the solutions of this system of equations. F with the subscript x is equal to 0 and f with the subscript y is equal to 0. Let's write this system. We have 4x to the power 3 minus 4y is equal to 0, and from here we have 4y to the power 3 minus 4x is equal to 0. We need to solve this system of two equations. From the first equation, we obviously have that y is equal to x to the power 3. And let's substitute this result in this equation. Let's see, what do we have? 4 times x to the power 3, then we take that term, and then we take that term to the power 3 is x to the power 9 minus 4x is equal to 0. That is, x to the power 9 minus x is equal to 0. Now, from this equation we obviously have x, and over here we have x to the power 8 minus 1 is equal to 0. We know from basic math that a squared minus b squared is a minus b multiplying a plus b. Let's apply this trick over here and let's see what do we get. We have x. In my case, a will be x to the power 4 and b will be 1, and consequently this term can be written like this. Is equal to 0. Okay, let's go further. Now, let's apply again this trick to this term over here. Let's do that. We have x to the power 2 minus 1 x to the power 2 plus 1 multiplying x to the power 4 plus 1 is equal to 0. This equation obviously has real and complex solutions. Complex solutions are usually solutions that can be written like this. C is equal to, for example, 3 plus or minus 2 times I, where I is the imaginary unit, that is the square root of minus 1. However, we are only interested in real solutions. This part can never have a real solution, and consequently, only this part can have a real solution. This equation can be also written as x, again using this trick, x minus 1 multiplying x plus 1, and that's equal to 0. From this equation we obtain, I will write it over here, x1 is equal to 0. That is, x is equal to 0, that's the first solution. Then, by using this equation, we can obtain that y1 is also equal to 0. And this is our first critical point. I will write it over here, 0, 0. Again, the critical point is the point for which these partial derivatives vanish. Okay, how about the second point? Obviously, from here I can have that x is equal to 1. When x is equal to 1, y is obviously equal to 1. I will denote this solution x2 is equal to 1 and y2 is equal to 1 from this equation. And we obtain our second critical point, and that point is 1, 1. How about the third critical point? Well, from this part I can obtain that x is equal to minus 1, and consequently, if I substitute in this equation minus 1, I obtain y that is equal to minus 1. Consequently, we have x3 is minus 1 and y3 is minus 1. And consequently, I have the third actually critical point, that's minus 1 and 1. To make this video tutorial as clear as possible, I erased the previous part and I summarized my critical points over here. The next step is to form the matrix of partial derivatives. This matrix looks like this. Here we have fxx. fxx is defined over here. Then we have fxy. It's defined over here, fxy, and then we have fyy. Let's form this matrix. Let's substitute the values and let's see what we have over here. We have 12 x squared from here, fyy will be 12 y squared from here, and the cross term is minus 4 and minus 4. The next step is to determine the determinant of this matrix. Obviously, determinant of this matrix, I will denote it like this since it depends on x and y, is equal to, let's see, I have 12x squared multiplying 12y squared, that's 144 multiplying x squared times y squared. And what do I have over here? I have minus 4 multiplying minus 4, that's 16. I have minus 16. And that's the determinant. So why is this determinant so important? Well, on the basis of the sign of this determinant for critical points and on the basis of the sign of this partial derivative for critical points, we will be able to determine if the particular critical point is maximum, minimum, or saddle point. In fact, I created a video tutorial whose link is given in the description below that explains this, and here's the main theorem. Here's our P matrix, here's the determinant, We basically computed it. However, this is just a general form. And then these three conditions are very important. If the determinant of our matrix P at the critical point is larger than 0, and if this fxx partial derivative evaluated at the critical point is larger than 0, then our function has a local minimum at the critical point. On the other hand, if the determinant is larger than 0, and if this partial derivative is smaller than 0 at the critical point, then the function f has a local maximum at the critical point. And finally, if the determinant is smaller than 0 at the critical point, then the function does not have a local minimum at the critical point, and it doesn't have a local maximum at the critical point. Instead, the function has a saddle, or actually has this point, the critical point is actually a saddle point of the function. We need to apply this theorem to our case, so let's do that. First case, I'll denote it here. Critical point 0, 0. Determinant of P of 0, 0 is obviously minus 16. Minus 16. Good. It's smaller than 0. Okay. But how about fxx? fxx, here it is. At 0, 0, obviously fxx at 0, 0 is what? Is 0. Let's go back to our theorem. Let's see the case. Determinant larger than 0. That's not our case. Determinant larger than 0. That's not our case. Determinant smaller than 0. This means that the point 0, 0 is actually the saddle point. And we will denote here that this is actually the saddle point. Good. How about the second case? Critical point is minus 1, minus 1. Let's see. Determinant P of minus 1, minus 1 is obviously, let's see, 144, good, minus 16. And I don't even need to calculate the result. I can immediately see that this is larger than 0. Good. So the point is definitely not the saddle point. However, we still need to see this term. So what's the value of fxx at the critical point minus 1, minus 1? Let's see. What do we have here? We have 12 multiplying 1, and as the result we obtain 12. And this is larger than 0. Okay, let's go back to our theorem and let's investigate the case. Determinant is larger than 0 and fxx is larger than 0. This means that our function has a local minimum at the critical point. Okay, so this critical point is local minimum. Perfect. How about the third case? Let's see the third case. The third case is 1, 1. Okay, let's see. Determinant of P 1, 1 is obviously 144 from here minus 16. Again, this is larger than 0. Perfect. How about fxx? Let's see. fxx is given over here at the critical point 1, 1. Again, it's equal to 12. And that's precisely the case we had before. Consequently, this is also the local minimum. Perfect. We solved our problem. Okay, that's all for today. I hope that you like this video. If you like the videos I create, please press the like and subscribe buttons. Thanks a lot.